Welcome to the stream with too many windows. It's understandable criticism that was leveraged. I have too many windows. But it's because I make complicated software. The project is still the now hilariously fast index. What was the wording before? Stupidly fast? No, ridiculously fast. It's different, very important terms of speed. And I upped the ante once more. Now we want to compress 70 gigabytes of data, which is the complete text of the English Wikipedia. And I have downloaded and unpacked, and it is 72 gigabytes. Oh, there are different counts. I read 768, I think. There are these two different versions of a gigabyte. Doesn't matter. It's around about 70 gigabytes. It's just the raw text, and I am compressing it by taking 100 million characters at a time, running it through my patented, not patented algorithm, and these 100 million characters end up as 31 megabytes. So we're doing this with the whole text in manageable chunks. And this is running in the background on the server. So overnight, it made some more compressed files. And this just makes me happy. Even while I sleep, the machine produces more content. So we're around about a tenth of the way done. Still 60 gigabytes to go. The idea is to combine the compression algorithm with suffix trees. Suffix trees are a very smart way of searching. Suffix trees. But they have disadvantages. The suffix tree is huge in memory. Here on the Wikipedia page, they actually have the complicated example already. The word to be indexed is banana. And in the end, there's a repetition, N-A-N-A. So you build this tree, you just go letter by letter, or you go the whole way if there are no branches anymore. So we go here, banana, end. Or we take a suffix, which is just this string. Drop the B and start with the A, so we follow here, A, get to this node, N-A, N-A, done. And this 1 here tells us that we have traversed the string starting from position 1, which is 2. Computers start with 0, sometimes, depending on the programmer's choice. So this is the suffix tree. If you look for any string contained in the word banana, you just start up here and travel through the tree. And this here, this line, this seems to indicate that this part of the tree is actually the same as this one, disregarding the numbers down here, which can probably just be calculated. They can actually have done this. This number 1 can be calculated from how far you went through the tree. It's not even difficult. You just count the characters you saw on the way. In this case, 1, 2, 3, 4, 5. The word has 6 characters, so we skipped 1. So the string position we started up here with was the position 1 in the original text. So if we try to merge these, and we would have a smaller tree, because as I said, they are big in memory. So if we store this naive tree, it's obviously bigger than if we use this edge and drop this part here. I'm not sure how much of a difference it makes, because there has to be a repeating string in the end. We are compressing Wikipedia, which is a huge long text, and it's not going to have a repetition at the end. At the end, they're going to be closing XML tags. So maybe this optimization here, there's another one of the same kind here. Maybe we just don't need it. I haven't found out how to implement it yet, how to find these connections here and how to make the thing work. So I have a tree that's like this. I made this kind of a tree, and it's actually pretty cool. I made something nice called managed int object. I manage my own memory in Java, because if you make a tree, it's going to consist of lots of little nodes, and nodes are each are a Java object normally. And Java objects have a header of at least 8 bytes, more like 12, I should think. Yeah, it's 12 for the 64-bit VM, which we're going to use. So we want to skip that, and we just make an int array. This is the integer array that everything is stored in, the whole tree. So obviously we have to make our own structures, we have to define what a pointer is, we have to do garbage collection in this managed space, we have to grow it if it's not big enough, and there's a list of free spaces, because we can also have to delete objects while we make the tree, so we have to manage where there's some new space. Look how compact this is in JavaX. A free list is a standard concept. It's really short code in JavaX, and B, it is like basically perfectly efficient. It has 2 different indices of how to remembering the free parts of the memory array. One is by length, and one is in order, just all the free parts and free ranges sorted, and they are all managed efficiently. And by this you can instantly find out where there is a free space of a required size. This is pretty good. That's JavaX style right there. Short and powerful, and usually quite efficient. So these are these objects, and there's a memory collector, a garbage collector, and compactor. This is here. It takes a lot of intermediate memory to run, which is kind of unfortunate. So if there are gigabytes of heap already, then you might not be able to compact with this current architecture, but we'll improve that too. So, and here is the actual suffix tree using these managed objects. And there's some clever object-oriented handling of these virtual objects that exist in the int array. There's a space class, and you basically just store the address in the int array, and then you have methods to access the fields. Memory get base address plus field offset. And you can even have lists which you convert on the fly. And you need to implement a method that tells the garbage collector which object is where, and the fact that you still need it, so you send it some notes here. Note that there's an object, note there's a pointer, note there's a pointer array, and you go through the children of the node and send them to the garbage collector. That sounded wrong. You send them to the collector, which notices that you still need some objects, after which the compression can run in the heap compaction, I mean. So this suffix tree, it works, but it seems really slow to build because it's the naive algorithm. If you have a string of, what do we have, 100 million characters, it will actually have 100 million iterations and add each of the suffixes to the tree. So it's up to n squared in runtime. It's less in practice, but it's still slow. I think I'm actually making one of these suffix trees, and it just doesn't end. Yeah, here. I started this last night. I can't cancel because I forgot to put in the code to make it cancelable. Oh, I can. Okay. It's a newer version. But it was running and running and running, and I think it had made... This is the other routine. No, it was a tenth of the way done. Just 10 million of these suffixes, which is way too slow. But suffix trees have been studied by smart people. For example, these guys, Mr. Yukonen, probably saying that wrong. LULZ has probably made the best algorithm. It's a linear time suffix tree construction algorithm. And it's online too, so you can add more to the string and it will process each character quickly. We don't need that part, but it's good that it's a fast algorithm. But as smart algorithms are, they're probably quite complicated. I found one implementation here from a Googler. The code looks nice, but it uses a lot of memory, and it does more than I want. Generalized suffix tree is multiple texts compressed into a suffix tree. I only have one text. So I searched around some more, and there's this master algorithm. Somebody immediately found a bug in this code, so hopefully with this bug it does the job. You saved my day. Sounds pretty good. So I put this into JavaX and I'm playing with it. It makes a small suffix tree with 5 characters, which leads to 9 nodes. That sounds about right. The number of nodes seems to be something like 1.5 times the length of the input string. In my super fast search engine that I still believe I can make, I will not put characters in here, but I will put symbols in there generated by the compressor. The compressor goes to the text, and if it finds repeated strings, words or whatever it is, or even sentences, it makes a new symbol for them. And over this list of symbols, which is shorter than the original character array, we run the suffix tree algorithm. So we combine this compressor and the superpower fast suffix tree search, because that might make it manageable. And if we cache only some parts of it, we can keep the whole suffix tree on disk. And that way we can get away with a machine that is smaller than 70 gigabytes in RAM. So in the end, I want to make an input field on a website that's called wikisearch.something. And you can search in Wikipedia, the whole text of Wikipedia, in like 1 millisecond, like really fast. I didn't find a search engine for Wikipedia. If you go to Wikipedia. Whatever it is these days, there's a search engine, but it only finds titles, right? Computers are... What does it do? Okay, this looks like title results. How many results do we have? 500 pages. Who knows? But it doesn't seem to be a full text search the way I mean it. Like you just would get a list of sentences that contain exactly this text. Because if you use it in a smart way, it could be a good thing towards AI. The AI would make some smart queries, and from the results make more queries. Obviously, is a limited way of searching if you can only search for exact strings, but it's a good basis for experimentation, I think. I just think this should exist, like a Wikipedia search engine. Yeah, okay. Does this work? Page computers are very doesn't exist. Yeah, I didn't find a proper search engine for Wikipedia, excluding Google. So I am making one. Let's check if there's new production of the server. Yeah, the server has made another new file. Just spit it out. Every 15 minutes we get a new chunk of compressed Wikipedia text. Enough space on disk? Yes. Alright. I'm probably trying to avoid the hard programming work, which is why I talk about anything and everything else. Programming really can be tedious, but somebody has to make the program, right? Something special about this implementation of the suffix tree is that there's this field. First of all, a node has a parent. I mean, in my implementation, of course, it also has a parent, but I don't store that because I optimized everything for a small size. So in my implementation, all I have is the from and to, which is the part of the original string that we are referencing, and a set of children. Not a map, but just a set, because you can look inside of each child and see the first character and sort by this. So no need to make it a map. This is already very, very optimized in size. But here this thing has a parent link. Maybe you need this for the algorithm. You could throw it out after the tree is made. But this confuses me. This is the regular child list map set whatever. The same as I have here. By the first character you index all the children of the node. I understand all that, but what is this? Every node has one link to a suffix. I'm really quite confused by that. So now, what do I have to do? First of all, I should check this algorithm, of course. I should run it through systematic tests. And then I'll optimize it for my object header free storage. This also allows it to be serialized on disk. That's pretty cool, actually. Which one was the one? NWIC 8. This is a short 100 million characters excerpt of Wikipedia. So it's like one of these packages that we are compressing. And I made a suffix tree already here. So it turns out 2.5 gigabytes for this input. But at least the nice thing is that the code automatically saves the whole int array to disk. And we can run it from disk, like virtually. That's the whole trick. We don't have to load this 2.5 gigabyte thing. We leave it on disk and the user types a character. And at that moment we search the tree on disk, which is just a few disk accesses, if it's not cached. And then we wait for the next input. And we can, at each step, we can return search results already. We are at some node in the tree and we can say, oh, this had 500 million and such results. It's a bit more involved because there's compression before it, but basically that's the thing. And if you want to get ahead of the user, you would just, at this moment where he has typed nothing or she, you would maybe go to all 26 characters and do the search proactively. So just search for every character the user would probably type. So, and then we have instant results, even not 1 millisecond, but instant. It's maybe overdoing it, but there should be ways to make this really fast. Yeah, so generating these suffix trees. It's a pity that algorithms are kind of hard to understand, algorithms of this advanced nature. It's not super long, I mean, the data structures are not that complicated, it's not super long, but I want to actually understand it, I think, or maybe not, I'm not sure. The time-consuming way is to go through this and really understand what it all does. Maybe I can do some half-baked version. I'll just make it work and roughly get what the structure is and call it a day. I just want to have the search engine running. Do this little magic trick. And I'm not completely sure if this is absolutely new. I think the method definitely is new. The results are probably new too. I don't know. Where is our Wikipedia full-text search engine? I haven't found one. Weird holes in the matrix. Build node. Yeah, enough streaming for one day. Thanks.